Sharing screen, usual thing. All right, let's do it. You know, there's been some discussion in the department about what good is scattering theory and should students learn it and stuff. And I've been thinking about that debate, you know, about it. And I think one of the advantages of learning scattering theory is that it teaches you things about wave fields in general, about how they behave, and, you know, things like diffraction and stuff like that. Which I think there's virtue in knowing that. I think there's a lot of virtue actually in knowing that, having some experience in that kind of stuff. I'm going to begin a little bit early because there's a few things to review from last time. Let's see. So this is kind of set up here. Let me get this, see if I can get this locked on screen here. All right, I hope that works. Yeah, so here's some summary from what we were doing. We've been working on central force scattering, which means potential is a function only of the radius. This allows us to separate the Schrodinger equation and talk about, for example, the radial wave function. One of the central objects in this theory is the phase shifts, which we call delta L. They depend on the angular momentum quantum number L. And they're defined by looking at the asymptotic form of the radial wave function. The radial wave function depends on K and L. K is essentially the energy, and L again is angular momentum. And at a large distance from the origin, where the potential is negligible, you got to have something that looks something like a free particle solution. And the phase shift delta L is basically the phase shift or the phase of the wave that you see out at a large distance relative to what you would see if there was no potential at all. In other words, relative to a free particle. So in fact, the delta L phase shifts are equal to 0 if the potential vanishes. But this is a formal definition of them. The Hankel function here is the free particle solution outgoing wave at large distance, well, at any distance as a matter of fact, but it's got the outgoing wave. The complex conjugate's the incoming wave. If you take the asymptotic form of the Hankel function, you see clearly the outgoing wave, e to the IKR, and the phase shift has been incorporated into the phase here. The I business out front is just a convention of the Hankel function. In any case, that's the definition of the phase shift. It's as I say, it's the phase of the wave out at large distances, out at infinity, essentially relative to the phase you'd have for a free particle. Then we find, after some substantial calculation, which I went through in last lecture, we find that the scattering amplitude f of theta can be expressed as a series over angular momentum. This L goes from 0 to infinity. It's the angular momentum quantum number of some things that are expressed in terms of the phase shift, the e to the I delta L and the sine of delta L. And then you got a Legendre polynomial. The scattering amplitude depends only on theta because it's a central force problem. If you put the beam direction in the z direction, then f is azimuthally invariant, doesn't depend on phi. In any case, the differential cross section is the square of the scattering amplitude, and you can square the series if you want and integrate over solid angles. And if you do, you get an expression for the total cross section sigma. It's 4 pi over k squared times a somewhat simpler sum. Again, this goes from 0 to infinity, which is expressed again in terms of the phase shifts. So if you know the phase shifts, you can calculate the differential cross section. You get everything you need to know. Now, let's see. These sums that are given here, by the way, are called the partial wave expansion of the various quantities. This is the partial wave expansion of the scattering amplitude, and this one of the total cross section. So that's general for any central force problem. What we did in the last lecture was we took an application, which is that of a hard sphere. Hard sphere is where the potential V of R is infinity out to a radius A. That's the radius of the hard sphere. The wave function, the radial wave function, has to start at 0 at the boundary of the hard sphere, and then it rises up, you know, and then oscillates to get far enough out. It oscillates. So these are the boundary conditions. And using those boundary conditions, it's straightforward to work out an expression for the phase shift. It gives you here is e to the 2I delta L. It's a ratio of Hankel functions which are evaluated at Ka. K is the wave number and A is the radius of the sphere. So it's an explicit formula for the phase shifts, but it's expressed in terms of Hankel functions. So in order to get something that's a little more easier to think about, we're going to take, we're taking, in the process of taking some limiting cases, namely the cases in which, first of all, the quantity Ka, which is dimensionless, is much less than 1, and then we'll take the case where Ka is much greater than 1. So we basically finished the case Ka is much less than 1 in the lecture last Thursday, but let me review what we found. So what we found was that, let me move this up. What we found was that there's only one phase shift that contributes. Oh, by the way, here's the picture of it, which is, here's the long wavelength waves coming in. By the way, Ka much less than 1 is the same thing as saying that lambda's the wavelength is much greater than the size of the scatterer. So here's the scatterer here. It's a little tiny sphere, small compared to the wavelength of this wave, which is marching in. In any case, what we found when we calculate the phase shifts and work things out is that only the lowest phase shift for L equals 0 is significant. All the others are much smaller. Other delta L are negligible. This implies, and that delta 0 is given by minus K, Ka, Ak, same thing. This implies that the scattering amplitude is simply minus A. Squaring it, we get the differential cross section, which is A squared. And then the total cross section, integrate this over all solid angles, becomes 4 pi A squared. So then there's a couple of notable things about this large wavelength solution. One of them is that the scattering is isotropic. As I explained, this is what we call S-wave scattering. S-wave scattering is general at low energy scattering, doesn't have to be a hard sphere potential. I gave some examples like in Bose-Einstein condensates where this occurs. S-wave scattering means that the only wave that's radiated from the scatterer is the S-wave, and therefore is isotropic, which, as you see here from the differential cross section, is independent of angle. So it's the scatter wave goes off in all directions with equal intensity. So that's a notable fact about this limit. There's another notable fact, which is that the total cross section is 4 times the geometrical cross-sectional area of the scatterer of this little hard sphere, which is over here. The total classical cross-section, if we think about classical scattering, sending a beam of particles at the hard sphere, it's just obvious that the total classical cross-section is just pi a squared. It's the cross-sectional area of the sphere, because anything outside that radius just goes straight through and doesn't scatter. So what we're finding is that in the small Ka limit, or let's call it the long wavelength limit, what we're finding is that the total cross-section is, in quantum mechanics, is 4 times as big as the classical cross-section. Now, the limit in which the wavelength is large, that's the quantum limit. That's where you expect quantum mechanical effects to be most important. Whereas classical mechanics ought to emerge in the limit in which the wavelength is small. We saw that in WKB theory last semester. So this limit we're taking here is the extreme quantum limit, not the classical one. So you might say it's not surprising that the answer turned out to be significantly different than the classical answer, in fact, by a factor of 4. Okay, so anyway, let's just post that as an interesting observation for this case. So then that's all I want to say about this case of a small sphere large wavelength small sphere scattering, unless there's any questions about it before I move on to the other case, which is the first topic for tonight. So any questions about this? If not, I shall find a clean pad of paper so I can go to work and set this sheet aside. So let's now then take the opposite limit. Let's take the limit where Ka is much greater than 1. This is equivalent to saying that the wavelength lambda is much less than the size of the scatterer. So let's make a picture of what we expect to find here. Let's say here's our scatterer like this. It's a sphere. It's not a bad sphere considering my lousy drawing talents. Radius of A. And the waves are coming in, and we want the wavelength to be small compared to the size of the scatterer. So let's draw it like that. They're coming in like this. Here's the K vector, like that. And so the waves come in, and what do? They hit the scatterer, draw it like this. That one hits the scatterer there, draw that one like that. That one hits the scatterer there, draw them like that. And then to go downstream, what happens is the waves kind of decouple from the scatterer. Why? Because they're creating, in effect, a shadow, you see? It looks something like this. That's roughly the idea. And then, of course, these waves that have hit up here produce scattered waves, which radiate. They have the same wavelength by conservation of energy, so they're scattered waves that go out various directions, like so. So this is kind of a picture of what happens. Now, these waves downstream from the scatterer, as I just said, there's a shadow in the middle, but they gradually diffract and fill in the shadow. And if you get into diffraction theory, it'll tell you how this happens and how far downstream you have to go. But eventually, in effect, the shadow, which is a hole in the incident wave, eventually it kind of anneals, it fills in because of diffraction. And the scattering cross section is defined in the limit that R goes to infinity. So the cross section doesn't by itself show a shadow. What it shows is, where particles were deflected. But in any case, this is what happens this is a picture of what happens to the waves. All right, so let's analyze this using our formulas. We had a formula, I think it was in the last page, but I'll copy it for you. The exact formula we got for the phase shifts was e to the 2i delta L's with a minus sign. It's the second Hankel function L of Ka divided by the first Hankel function L of Ka. These spherical Hankel functions are just J plus and minus Iy. They're the linear combinations of the two types of spherical Bessel functions, which are the radial solutions for free particles. I prefer the Hankel functions for the large asymptotic limit. R goes to infinity, because the H1 is an outgoing spherical wave, and the H2 is an incoming spherical wave. They have fairly simple asymptotic forms. In fact, allow me to bring back my last page and tear off the front page, because this gives us the free particle solutions. Here are the two Hankel functions. They're J plus and minus Iy. So the complex conjugates of each other. There's a conventional phase factor out front. It's this I to the plus and minus L plus 1. And otherwise, basically what you get is either the IKR over KR, an outgoing spherical wave, or its complex conjugate, which is an incoming spherical wave. That's what these two things are. And in this formula for the phase shifts, they're evaluated at Ka, because that's where the boundary conditions were on the wave function. This is where this came from, is demanding the wave function vanish on the boundary. All right. However, we want to evaluate this in the limit that Ka is large. So that's the same limit I had on that previous page I just showed you. So this turns into the minus sign, and in the numerator we have I to the L plus 1, and then we've got e to the IKA divided by Ka. That's the numerator. And then the denominator is I to the minus L plus 1. Oh, the numerator should have been a minus IKA. In the denominator, we get e to the plus IKA divided by Ka. And so we just evaluate that, and you can see the factors of Ka are going to cancel each other. Do it in red. I don't know if you can see that very well, but that's in red. They cancel. As far as the I factors are combined, we'll combine those together. We get a minus 1, get I squared is minus 1, get I to the L plus minus 1 to the L plus 1 power with a minus sign out front from here. And then we get e to the minus 2 IKA. And minus times minus the L plus 1 is the same thing as just minus 1 to the L. And that's the same thing as e to the I L pi. So let's write this whole thing then as e to the I L pi minus 2 IKA. Okay? And now if we take the logs of both sides to solve for delta L, take the logs and divide by 2I, what we get is that delta L is equal to L pi over 2 minus Ka. And let me box that, because that's the formula, explicit formula for the phase shifts and the limit where Ka is very large. Now, these formulas that I used here, these asymptotic forms that I put in here, are actually only valid if Ka is much less than L. So I'll make a point about that. But if K is much less than L, then these are valid and this is the correct result. So what this tells us then is that for small L anyway, as long as K is much, wait. Let's see. I didn't say this right. This is, yeah, I'm sorry. I didn't say this right. This is Ka much greater than L. It's not sufficient that it just be much greater than 1. It has to be much greater than L for these asymptotic forms to be valid. That's what I want. All right. So the K is much greater than 1. We're assuming that that's the short wavelength limit. But to invoke these asymptotic forms, we in addition need Ka is much greater than L. So what that means is when L is small, this formula is valid. And the phase shift basically advances by just a pi over 2 every time L notches up by 1. So we're going to get expression. Let's look at the total cross section. The general expression for the total cross section was 4 pi over K squared times the sum on L of 2L plus 1 times sine squared delta L. This is an exact formula for this is a partial wave expansion of the total cross section. This goes from L equals 0 to infinity. However, as I explained last time, there's actually an L max beyond which there's an effective cutoff. And L max is of the order of Ka, which is a large parameter we have for this problem, for this limit that we're studying here. So we have a finite sum, but a large number of terms that need to be summed up in order to get the total cross section. It's not too hard to make a reasonably accurate estimate of what this sum is. We do it in the following way. Let me draw the complex plane here with the real and imaginary axes, and I'll put the unit circle in here like this. And then let's plot the numbers e to the I delta L, these phases e to the I delta L, which then of course become points on the circle here, and the delta L is the phase angle of the point. So since delta L starts off at minus Ka and then just increments every time L goes up by just pi over 2. So it starts off somewhere, and then it's going to increment by pi over 2, and then another pi over 2, and then another pi over 2, and then it'll come back to where it started from, and it'll just keep going around these 4 points. Except what happens is when L starts to gets to be bigger, when L starts to get to be bigger, then it starts to get closer and closer to Ka, which is the cutoff of the sum. Then the increment, I'm not proving this, but the increment decreases somewhat from pi over 2 and gets smaller and smaller. So what happens is you start to get a phase lag here coming in and going around the circle like this. And you get these points that fill in the circle like this. And they're now orbiting with increments that are less than pi over 4. But in any case, they fill in, going around and around the circle, filling in dots like this, until we reach the value, the fairly large value of Ka, at which point the series cuts off. Now, as long as these phase points are orbiting the circle like this, then the average value of the sine squared is just a half. So that allows us to simplify this sum by just replacing that. So if we do this, and what we get then is that sigma, just making rough estimates now, the sigma is in the 4 pi over K squared. I'll take the 1/2 out of the sum. We'll take the L equals 0 up to, let's call it capital L, which is the same thing as L max. So capital L is equal to Ka, or the nearest integer to Ka, of the quantity 2L plus 1. Now, what we're really summing here now, you see, is a sum of odd integers, 1 plus 3 plus 5, and so on. And that sum is equal to the square. So in fact, this sum can be done exactly, and it turns into L plus 1 squared. But L is large, so here for simplicity, we'll just replace it by L squared, because L is much greater than 1, because L is equal to the same thing as Ka. So doing all that, then we put in sigma then is equal to 4 pi over K squared times a half times the quantity Ka squared. And you can see that the K's will cancel here. And what we get is we get a total cross section with sigma, which is equal to 2 pi a squared. And that's the main conclusion. And in fact, a more detailed and careful analysis of this sum shows that in the limit in which Ka becomes very large, the total cross-section does indeed approach 2a squared. This estimate is actually correct. In fact, it's exactly correct in that limit. Now, this is the opposite limit that we looked at before. This is a short wavelength limit, which ought to be the classical limit. But the classical cross-section for scattering from a hard sphere is the cross-sectional area, which is only pi a squared. So we weren't dismayed when the extreme quantum limit gave us an answer that was off by a factor of 4 from the classical result. You'd expect it to be different. But in the short wavelength limit, we'd expect them to be the same. And they aren't the same. They're different by a factor of 2. And the question is why? Why is the quantum cross-section in this short wavelength limit twice the classical cross-section? What does that mean? So what I'd like to do now is explain to you what that means. Now, we haven't calculated the differential cross-section in the large Ka limit. All we've done is calculate the total cross-section. In the short Ka limit, we calculated both of them, and we found the differential cross-section was constant. Remember, it was isotropic scattering. That's S-wave scattering. Let's look at the classical cross-section. What is that classically? So classically, I've got a sphere like this, and I'm sending in a beam of particles, and they all have the same momentum. And what do? Well, one comes here and bounces off like that. One comes in straight at this end and bounces straight back. This one comes in here and bounces like that. One comes in here and bounces off like that. One comes in here and bounces off like that. So you get out scattered particles that go out in all directions, including some that go in the forward direction. If you miss the sphere altogether, you go straight forward, like so. Well, it's straightforward to work out the differential cross-section d sigma d omega classically. It's easy to do. You just do specular reflection on the surface of the sphere. And what you find is that it's a squared divided by 4. And that means the total classical cross-section. Now, so it's a squared divided by 4, and in particular, it's independent of angle. So the classical cross-section is isotropic, believe it or not, scattering off a hard sphere. So that means the total cross-section is just 4 pi times that, which is pi a squared, and we knew that had to be the right answer for the classical problem. Okay. So we've got a differential cross-section for the small Ka limit and for the classical calculation. And we have a total cross-section only for the large Ka limit of quantum scattering, which ought to be the classical limit, but evidently is not. So let's see if we can straighten this out. So let's make some plots of differential cross-sections then. Let's plot d sigma d omega, and we'll have different versions of sorry. I want the d sigma d omega up here. Let me draw a line here. And let's divide it by a squared so it becomes dimensionless. And on this axis, let's put the angle theta, and let's put pi out here, which is the maximum scattering angle of theta. This is backscattering here.
Excuse me. I think I'm actually confused by something fairly simple, but I figured I'd ask now before that snowballs. So what actually is omega here? Because we're saying that sigma classical is not dependent on omega, but if I'm imagining omega as the solid angle that the sphere is taking up, then that's related to the radius of the sphere, right?
No, the angle refers to the direction of the scattered particles. It's defined in the, I mean, this is a hard sphere, so the particles are free after they bounce. But in general, the cross section is only defined in the asymptotic limit. You look at how many particles a distant collector, accumulates per unit time. That's the counting rate, and you divide that by the incident flux. Now that detector subtends a small solid angle, and so the answer is d sigma d omega times that delta omega.
Oh, gotcha. Okay.
That's the definition of cross section, and that's what this omega refers to.
Right. Okay.
Thanks.
Thanks.
In the case of this classical cross section, you imagine you've got a detector out here, which is looking at some direction. That's the theta and phi that are inherent in the capital omega here, and it's counting particles that are coming in. So you can see the particles that it's going to be counting are going to be ones that are coming in from a fairly narrow range of incident, impact parameters. It looks something like that because they're going to then bounce out in the direction of the collector.
Okay, that makes sense.
Got that? All right, good. All right, now So what we know is that so this, let's make this 1 here. So this is 1/2 and this is 1/4. So what we've just learned is that the quantum cross-section, differential cross-section in the small Ka limit is equal to, this ratio is equal to 1. And the differential cross-section for the classical limit, it's not a classical limit, it's classical calculation, because the limit doesn't agree with it. So this is the classical calculation. The differential cross-section is a²/4. It's 1/4 here. So on the other hand, what we also know is that in the case of Ka much greater than 1, which ought to be the classical limit, we find that the total quantum cross-section is 2πa². Well, for the classical cross-section, this area here is πa². You see, that's the total cross-sectional area of the sphere. So in the large Ka limit, the short wavelength limit, in other words, we have twice as much cross-section as we ought to have. And the question is, how is it distributed in angle? This extra cross-section, is it uniformly distributed in all angles, or does it have an angular dependence? How does it look? Well, it's a funny situation, actually. It's a tricky situation. If I take some angle theta here and I fix it and look at what happens, if I have small Ka, then the differential cross-section divided by a² is definitely equal to 1, just this point here like this. If I then, however, increase the value of Ka, what happens is it moves down, and approaches the value of the classical cross-section, namely 1/4 a². If I take a different angle theta here, and I do the same thing, and look at the cross-section, the quantum cross-section at small Ka, and then allow Ka to increase, again, it will go down, and approach the classical value of 1/4 a² at this angle. In other words, this entire line, if I increase Ka, moves down and approaches the classical line. So how can you get the extra cross-section? Well, the answer is that this approach is not uniform. It approaches more quickly at larger angles. As the angle gets shorter, the scattering angle gets smaller, it takes a larger and larger value of Ka to push the cross-section down. And the amount of Ka that you need to do to push the cross-section down to the classical value actually starts to approach infinity as you come closer and closer to the forward direction. So if we plot the differential cross-section at some large but non-infinite value of Ka, what you get is, out here at large angles, you get essentially the classical cross-section. As you move into smaller angles, you start to get small oscillations going up and down like this. I can sketch this very well. And the oscillations get bigger as you come in, like this. And then what happens is they do this. They go boink, like so, and they go way up like that. You get a forward peak here, like this. And this forward peak has a total contributes to differential cross-section of another factor of πa². So that's where the extra πa² came from. It comes from a huge enhancement in the differential cross-section in the forward direction. So the quantum cross-section approaches the classical cross-section at all non-zero angles theta, but the value of Ka that you need to go to make that happen gets bigger and bigger the smaller the angle gets. What one might say is that in the limit that Ka really goes to infinity, is you get the classical differential cross-section at 1/4 a² plus a delta function in the forward direction. So what's the physical meaning of this forward direction? Well, the answer is it's the diffraction. It's the diffraction or the bending of these light waves, or these aren't light waves, bending of these waves around the shadow, gradually closing in. Because the direction of these waves is changing, I mean, they have little hooks in them that do this kind of a thing as the wavefronts kind of move in, and you get wavefronts whose direction is changing. The wavefronts actually end up changing their direction, so they're pointing inwards, like this, to close the shadow. And so in quantum mechanics, that counts for the cross-section. And as I just explained, that cross-section actually doubles the total cross-section. So this is diffraction. Okay, I think that's all I wanted to say about this. This high Ka limit, the so-called classical limit. Are there any questions about this? If not, then we'll move on to the next topic. Next topic is the optical theorem. So this is the last topic on a list of general topics I want to cover on general scattering. So the optical theorem says this is applied now to quantum scattering. And it does not require that the scatterer be spherically symmetric. So we don't have to deal with central force scattering and phase shifts anymore. That's all specific to central, excuse me, to central force scattering. What the optical theorem says is that the total cross-section sigma in the optical theorem in this context is given by the quantity 4 pi over k times the imaginary part of the scattering amplitude in the forward direction. This is an exact result, and it's ultimately related to conservation of probability. So in the particle physics biz, they refer to it as unitarity. This is a consequence of unitarity. Notice that sigma itself involves the square of the scattering amplitude. D sigma d omega is that square, and you integrate over all angles and you get the total cross section. Whereas on the right-hand side, we have the scattering amplitude, which is not squared. And moreover, it's only in one direction, namely the forward direction. So it's a remarkable formula. It also has a number of generalizations, which I'll say more about, but when I'm finished describing how this works in the case of scattering of Schrodinger waves. So let's talk about scattering Schrodinger waves from potential, we will, so let me draw the potential here, X, Y, and Z. But as I say, we won't assume the potential is rotationally invariant, so it could be some lumpy object here near the origin, like so V of X. Let's send in a wave in the Z direction like this. Let's set K is equal to K times Z hat, like this. And here's our wave coming in like this. Okay. Now, the optical theorem is trivial to prove for central force scattering. All you need to do is just take those expressions for the scattering amplitude as an expansion in partial waves expressed in terms of the phase shifts, and the similar expression for the total cross section, which I showed you earlier this hour. And you just take the imaginary part of F in the forward direction, and you can just easily check that this formula is true. So I won't do that, because it's straightforward, and also because it doesn't give you any insight into what this formula means. The proof I'm going to give you now actually does give you such insight, and that's the advantage of doing it. So the proof I want to give now, which also applies when V is not necessarily rotationally invariant, is based on currents. Let's recall that the current is given by the real part of the quantity, which is the imaginary, it's a complex conjugate of the wave function psi of x times the operator minus I h bar gradient over mass m times psi of x. This is for kinetic plus potential problems only, because in the middle here you see is the velocity operator. Anyway, this is the definition of it. And the current satisfies the continuity equation. Let's do it right. Continuity equation is del dot J plus partial rho with respect to t equals 0. However, the solutions that we're talking about here, psi of x, are actually energy eigenfunctions. And that means that they're stationary states, and that means that rho is independent of time. So this goes out, and the continuity equation just turns into the fact that the divergence of the current is equal to 0. And as a result of that, by applying Gauss's theorem, we can integrate the current over a surface. If we integrate over any surface, this is understood to be a closed surface of J dot dA, the answer is equal to 0. This, of course, just means that if you have any closed surface, then the flux of particles which is entering that surface is equal to the flux of particles exiting the surface if we have an energy eigenstate. As I explained last time, those energy eigenstates correspond to the steady states of flux that you would see in a classical problem. So this is a very plausible result. All right, but it's rigorously true for this definition of J. The J of this quantum problem. Now, the surface that we're going to be interested in is a sphere of large radius surrounding the scatterer. Let's call it radius r, and we want to take the limit that r goes to infinity. We want to look at this in the we want to look at J in the asymptotic region and integrate over the surface of the sphere. So if we do that, then the total integral over the surface of the sphere has got to be 0. Now let's write out the wave function psi of x. Since we're so this consists of an incident wave, which is e to the I k dot x, plus a scattered wave, and the scattered wave is e to the I. Its asymptotic form is e to the I k r over r times the scattering amplitude f of theta and phi. I shouldn't put an equal sign in here. This is an asymptotic form. Let me put it this way. So this applies when r goes to infinity. The incident wave is the same for all values of incident wave is the same everywhere, but has the same formula everywhere. But this is only a leading asymptotic form for the scattered wave. Nevertheless, we're interested in integrating over a large sphere as r goes to infinity. So that's exactly the place where we need to evaluate J, is in the asymptotic region. So let's do that. Let's evaluate J and let's do the integral. So let's write this out then. J then is equal to, if I take these wave functions and plug them in here, what I get, J is equal to the real part of, just to write it out explicitly. Oh, by the way, the e to the I k dot x, let's write this as e to the I k z, using the fact that our wave is in the z direction here. Let's do that. And by the way, z is equal to r cosine theta. So this is the same thing as e to the I k times r cosine theta, if you want to write it in another form. All right, anyway, let me write the psi of x, let me write psi star of x first. So it's a star of this thing. So it's e to the minus I k z plus e to the minus I k r over r times f complex conjugated. F depends only on angles. Then we have the operator minus I h bar gradient over m, the velocity operator. And then I have psi without the star. So that's e to the I k z plus e to the I k r over r times f. And we get this expression like this. Now then, this has 3 major terms. There's an incident flux that comes from the e to the I k z on the 2 sides. There's a scattered flux that comes from the spherical waves, e to the plus minus I k r on the 2 sides. And then there are cross terms. So let's write this as J incident plus J scattered plus Jx, which x stands for cross terms. Let's write it like that. All right. Now, J incident is easy to work out. It's just equal to the real part e to the minus I k z times minus I h bar gradient over m multiplying on e to the plus I k z. And the gradient is going to bring down, k times z hat. And I times that. The I minus I will cancel. H bar k divided by m is the same thing as the velocity of the particles. And the real part goes away. You don't even need the real part because the e to the plus minus I k cancel each other. So this just turns into the velocity v times z hat. All right, so that J incident is easy. Now, what about the scattered flux? The scattered flux is equal to the real part of e to the minus I k r f complex conjugate over r times the velocity operator minus h bar gradient over m acting onto the e to the plus I k r over r times f. Now we did this calculation earlier in calculating the scattering flux when I showed you that the differential cross section was the square of the scattering amplitude, f squared. That was the result of that calculation. So I won't go through the calculation of the flux again, but this turns into the following, turns into v times the radial direction r hat times the absolute value of f squared, and the whole thing gets divided by r squared. to get this result, we need to take only asymptotic forms. That's to say, in this gradient operator, there's both radial and angular derivatives, but we drop the angular derivatives because they're higher order in 1 over r. They involve 1 over r times angular derivatives. Likewise, these expressions in these first and third blocks here are themselves only the leading term of an asymptotic expansion. So I really shouldn't say J scattered is equal to this. I should say it's asymptotically equal to this. There are higher order corrections. However, notice that those higher order corrections are going to fall off more rapidly than 1 over r squared. And so when we integrate J scattered over a large sphere of radius r squared, these corrections will just go to 0 as the radius of the sphere goes to infinity. So this term that I actually have calculated is the only one that's going to give a non-zero contribution to the final answer. All right. Now, if we draw pictures, then so now what we have is we have then an integral over this large sphere of J incident plus J scattered plus J cross terms dotted into the area element dA must be equal to 0. All right, and that's rigorously true.
Professor, can I ask a quick question?
Yes, sure.
So could you repeat one more time what you said about J scattering? Because you were saying that as R goes to infinity, it looks like J scattering will go to 0. So I don't understand how that's the only term that would.
It does, but you see, we're going to integrate it over a sphere of a large radius.
Oh,
And
okay.
and the area of the sphere grows as r squared.
Right. Okay. I understand. Thank you.
And so that's why anything that dies off more rapidly than 1 over r squared is going to give you a 0 integral in that limit.
Okay.
Yeah.
Thank you.
Yeah. That's why we only need the leading terms of both these things in these square blocks, as well as the leading term of the Laplacian operator. That's all we need. Excuse me, it's not Laplacian, the divergent, the gradient operator. All right. Okay, so, and of course, F squared is the same thing as d sigma d omega. So let's take a look at what this looks like. Let's draw a large sphere like this. Now, if you take the incident flux, if I take the z direction going like this, then the incident flux just looks like this. All the particles are, the flux just goes straight through. And I think this makes it clear, in case you don't want to do the calculation, that the integral over the sphere of J incident dA dot dA is just equal to 0. The incident wave doesn't contribute to the flux. Just as much comes out as goes in. What about the scattered flux? Let's take the integral over the sphere of J scattered dot dA, SCATT dot dA. Well, the dA is the element of area of the sphere like this. Here's the dA, it's a vector pointing outwards like so. So the dA as a vector is equal to r squared d omega, which is the magnitude of it, times r hat, which is its direction. So when I multiply this by J scattered, which is also in the r hat direction, then the dot product of the r hat just gives me 1. And you can see the r squared in the dA cancels the r squared in the denominator. And so this then, let me bring it down here so you can see where it is. Maybe you can't see where it is. I need to bring paper up. This integral then becomes equal to the integral over d omega of the velocity v times f squared, which is d sigma d omega. We worked that out earlier. And then everything else cancels, the r hat and r squareds go away. And so you see this gives us v times the total cross-section sigma. Now, the fact that the integral of the scattered flux should be proportional to the total cross-section is kind of no surprise, because you've got this scattered flux you see coming out of this scattering problem, maybe different amounts in different directions. But this integral had to give us a positive amount and had to be proportional to the total cross-section. This is just what we get as v times sigma. Now, given the fact that the integral of all three of these terms over the sphere has to add up to 0, and the incident flux gave us 0 as well, it follows that the integral of the interference terms from the cross terms in the flux has to give us equal and opposite to the integral of the scattered flux. In other words, this Jx must represent a flux of incoming particles from some direction here, which compensates for these outgoing particles. And so now, before we do the calculation, I ask you to sort of ask yourself, think about it a little bit, where do you think these particles are coming in from? Are they coming in from the incident beam? Are they coming in from all directions simultaneously? Are they coming in from the forward direction somehow, as if there's a source down there? They have to be coming in from somewhere. Well, let's find out. Okay, so here's how we do it. We do the calculation. It's a bit of a calculation. So it works like this. First thing to do is just get serious about writing out let's see, where I actually wrote it out already. Here is the total J. So now we want the cross terms. The cross terms are going to involve the e to the minus ikz and the plus ikr over there, and then the e to the minus ik over there and the plus ikz over there. So let's write these out. So if we do this, then the cross flux then is equal to the real part, and there's going to be two terms. And one is e to the minus ikz, and then we've got minus IH bar gradient over m, multiplied onto e to the ikr over r times f theta and phi. And then we add to this plus e to the minus ikr over r times f star of theta and phi times minus IH bar gradient over m times e to the ikz. All right. Now then, if we do these gradients here, and we'll just again take the leading asymptotic term if we do so, when it acts on this e to the ikr over r, what we get is we get the real part of e to the minus ik, and I'm going to write ikz is e to the ikr cosine theta, that part there. And what this gradient operator does is it brings out the velocity, and it leaves the e to the ikr over r like this, and f of theta and phi, and the direction is r hat, it's in the radial direction. And for the second term, then I get e to the minus ikr over r times f star times this derivative here, which gives me, again, the velocity v times the gradient in the z direction, brings out z hat times e to the ikz. Okay. Now we got the real part of the sum of two complex numbers. It's convenient to combine these together, and we can do so because the real part of a complex number is the same as the real part of its complex conjugate, because the complex conjugate only changes the imaginary part. So I can change the second term into its complex conjugate without changing the value of the result. And if I do, I get e to the plus ikr over r here times f of theta and phi without a star now, times velocity v times z hat times e to the minus ikr cosine theta. Okay, for that term there. And if I do that, then these two terms now are the two terms in question. They have a lot of factors in common. So what we get is velocity v is real. I'll bring it out. So it's a v times the real part of what? We have a common factor of e to the ik r times 1 minus cosine theta. It comes from here and here in the first term, and it comes from there and there in the second term. The velocity we already took out, so I'll circle that as well. We have a common factor of f, so I'm going to circle that, f there and f there. Let's put that in, f of theta and phi. We have a common factor of 1 over r, so let's put that in. We divide this by r. And then what's left is the unit vectors. We've got r hat here and z hat there. Let's put this as r hat plus z hat. Okay, so this is jx. All right. Now we want to dot this with the area vector dA, which, as I've explained, is r hat times d omega times r squared in order to do the integral. And let's look at the vectors first. So you got r hat dotted in r hat plus z hat. Well, that's the same thing as 1 plus cosine theta. Because r hat dotted in z hat's just cosine theta. The r squared here and the 1 over r there are going to combine together to give us overall r. So to simplify this a little bit, so then then to write this out, then what we get is the integral over the sphere of jx dot dA is equal to the real part. Let me bring the velocity out first. Here's the velocity here. Then we have the real part. Then we have the integral over solid angle d omega. Let's see if I have room to do this. We have e to the ikr times 1 minus cosine theta. We have f of theta and phi. We have 1 plus cosine theta. And I forgot the overall factor of r, which I'll bring out here. There's the factor of r. That came from the 1 over r in the denominator and the r squared in the numerator. Gives an overall factor of r. So let me try to separate this off because this is the integral we need to look at. Okay, so it's a little bit complicated to derive it, but here we are. Now we need the value of this integral in the limit that r goes to infinity. And since it's multiplied by r like that, you might think the answer is infinite, which of course wouldn't make sense. However, the integrand has got a factor of r there as well, e to the ikr. And as r gets larger and larger, this exponential function oscillates more and more rapidly. That's to say, it takes a smaller and smaller increment in theta to make an oscillation. The rest of the integrand doesn't involve k. It's fixed functions of theta. There's also a theta in the Jacobian here, the sine theta d theta inside that omega, but that's the same story. So as r gets large, none of these other factors depend on r. As r gets large, in effect, the wavelength of the oscillation in theta gets smaller and smaller. And so the integrand gets chopped up more and more finely by this oscillation, and that tends to make the integral go to 0. So this factor tends to make it go to infinity, and the oscillations tend to make it go to 0. And there's a question of how do these two tendencies compete with one another? Turns out the oscillations win. And the way to see that is to do an integration by parts. But to allow me to write this, and to do the integration by parts, let me write out the integral d omega explicitly, and maybe I'll write it as a single neat formula here. So the integral we get then is equal to v times r. That's these first two factors here. The real part of integral from 0 to 2 pi d phi. The integral from 0 to pi sine theta d theta. And then I'll write e to the ikr times 1 minus cosine theta. And then we have f of theta comma phi times 1 plus cosine theta. Okay, there's your cross, the flux from the cross terms in the asymptotic region. All right. Now let's take this, we're going to integrate by parts. Let's take this sine theta times this e to the ikr cosine theta. Let's notice that we can combine those together and write it as dd, write it as 1 over ikr times dd theta of e to the ikr 1 minus cosine theta. Just by the chain rule, the derivative minus cosine theta sine theta gives us a sine theta there. So these two red circle terms can be replaced by this. Now, if we do this, the r in the denominator there will cancel the r in the numerator. So that gets rid of this leading factor of r, which was annoying for us. And then as far as the rest of it is concerned, we can integrate by parts. So let's do that. So what we get then is the velocity times the real part of the integral from 0 to 2 pi d phi And then the rest of this is an integration by parts. So we get 1 over, well, let's do it this way. There's a 1 over ik, which I'll take out. That's this denominator here. And then the rest of it has 2 parts. It has e to the ik r. There should have been an r here, e to the ik r. E to the ik r, 1 minus cosine theta, times f of theta comma phi, times 1 plus cosine theta. And this is evaluated between pi and 0. That's the angular integration here. Minus the integral from 0 to pi d theta of e to the ikr, 1 minus cosine theta, times d theta applied to the rest of the integrand theta phi times 1 plus cosine theta. Close that, close that. So this is integration by parts. Now then, let's look at this at the second integral, the integral that remains here. We want to understand this in the limit that r goes to infinity. The analysis is similar to what we did before, except there's no prefactor of r out front anymore. So what this means is the chopping up effect due to this rapidly oscillating exponential. It oscillates more and more rapidly as r goes to infinity. It means that this integral goes to 0 in the limit as r goes to infinity. As far as what's left is concerned, that means the theta integral is now done, and all we need to do is to evaluate it between pi and 0. But it vanishes at pi because 1 plus cosine theta is equal to 1 plus minus 1 when theta is pi. So it only has a value at the lower limit. So this thing can be written this way as v times the real part of the integral from 0 to 2 pi d phi. I'll keep that part. Then we have 1 over ik. That stays the same here, that factor. Then we have a minus 1 coming from the fact that we're evaluating now at the lower limit. And then what we need to do is just evaluate this whole thing at the lower limit and see what it is. Well, at the lower limit, theta is equal to 0, so cosine theta is 1, so e to the ikr 1 minus cosine theta just goes to 1. 1 plus cosine theta goes to 2, so I'll put a factor of 2 in for that. And f of theta and phi gets evaluated at theta equals 0, which is otherwise the North Pole. At the North Pole, it doesn't depend on phi. Let's just write f of 0 for that, meaning f evaluated at the North Pole, okay? Now, so we can clean this up then. This becomes v over k. I'll take the 2 out times 2. And then we've got the integral from 0 to 2 pi d phi is just going to give us a 2 pi. You see that comes in because now nothing depends on phi anymore. Phi integral gave us 2 pi. Minus 1 over I is the same thing as I. So we get the real part of I times f of 0, like so. And I think that's it. The real part of if of 0 is the same thing as the imaginary part of f of 0, except with a minus sign. So this thing becomes equal to 4 pi over k with an overall minus sign, the imaginary part of f of 0 times the velocity v. And this has got to be equal to, by a previous analysis, of minus sigma times the velocity v. If we cancel the velocity v and we cancel the minus signs, we obtain the optical theorem that sigma was equal to 4 pi over k times the imaginary part of f of 0. So there's your optical theorem. Okay, nice derivation of it. Now, one of the things that this detailed in, so there's some technical manipulations of integrals and stuff to get this, of this cross term from the current. But this shows you that the current, which is coming back in, the incident current doesn't contribute anything. And the outgoing current is from the scattering process, so there has to be some current coming in. And that current is purely from the interference between the scattered wave and the incident wave. And moreover, what the evaluation, this integral shows you is that it's coming in from the forward direction. That's where the interference is taking place and causing the backward flux. By the way, in the case of the hard sphere scattering, where we had that shadow is a cancellation between the incident flux and the interference with the scattered flux. Believe it or not, that's what it is. It cancels out almost completely inside the shadow zone. Anyway, because there's no light there, so they had to cancel. Something canceled it. It's not the incident flux anymore. All right, so this in fact is a kind of a in fact, in the limit that the radius goes to infinity, the angles over which this return flux comes in from the forward direction get smaller and smaller. So it turns into a delta function in angle space. It's an interesting sort of a thing. It's a delta function in current flux now. It's an interesting sort of a thing because it's actually reminiscent of what happens with magnetic monopoles. You know, a magnetic monopole is a hypothetical particle where the magnetic field goes out like this. And this violates the Maxwell equation del dot B equals 0 because, you know, you've got a divergence from a point. But you can save the Maxwell equation if what you do is you bring in a long thin solenoid. And the long thin solenoid has condensed lines of magnetic flux that are coming in like this. And when they get to the end of the solenoid, they're so happy, you know, to be out in free space that they just explode and go out in all directions equally like that. So now that saves del dot B equals 0, but now you've got some return flux coming in. Well, that's kind of what happens with the current in a scattering problem. There's a return flux, but it's coming in from the opposite direction of the K vector. The incident wave is coming in like this, the outgoing flux is like that, and the return flux comes in the forward direction. What's the optical theorem good for? Well, one of the things, it's good for a lot of things actually. This is a fairly simple version of the theorem. The theorem has many generalizations. It generalizes to scattering of electromagnetic waves, of gravitational waves. It generalizes to inelastic scattering. Let me talk about inelastic scattering. Inelastic scattering is common in quantum mechanics. It's if you have let's say an A plus B reaction where two particles A and B collide. When they go out the other direction, the A may end up in an excited state. I mean, for example, if they were two atoms, both in the ground state, after the collision, it's possible that some of the collisional energy was used up to raise one of the atoms into an excited state. And if so, you can get a reaction like this. Of course, at the same time, you may also have outcomes where it's not an excited state. If so, then the place where they go out without changing the internal state, this is called elastic scattering, and the other is called inelastic. It's inelastic because some energy is used up, or maybe freed up, it depends on circumstances, in order to change the internal state of A. By the way, the internal state of A could be something like I just mentioned, like raising an atom to an excited state, but it could be something simpler too. These might be scattering, let's say, an electron off of an atom. A might be an electron. Let's suppose the incident beam is polarized, the electron is spin up. Well, the elastic channel, these are called channels, by the way. The different possible outcomes are called channels. The elastic channel is one in which the outgoing electron is also polarized up. But the electron might undergo a spin flip as a result of the interaction, in which case you've got an inelastic channel. So this is another example of where this could happen. All right. Now it turns out that the generalization of the optical theorem when there are inelastic channels is that the total cross-section sigma, the total sigma gets replaced by the total cross-section sigma over all channels. Is 4 pi over K times the imaginary part of F of 0, but only the elastic part. So this is how it generalizes, is that sigma becomes a total cross-section over all channels, but the scattering amplitude in the forward direction is only the elastic part. The reason for this is that you can't get an interference between the elastic part means the scattered wave, which is in the same quantum state, internal state as for the initial wave. If you have an inelastic channel, then you can't get an interference between the incident wave and the scattered wave. For example, an electron polarized up and electron polarized down, they don't interfere with each other. We want to talk about the state of a single electron. So you might have an electron pass through a magnet or something, it flips its direction of spin, and then the mirror bounces it back, so the two beams cross each other. You don't get oscillations in the probability distribution in that case. They don't interfere with each other because they're in opposite states like this. You work out the current and everything, you'll see that's true. So the elastic channel can only interfere with the incident beam can only interfere with the elastic channel and not the other outgoing channels. Now, what does this formula mean? What does it tell us? Well, one thing it tells us is that it's impossible to have scattering, which is purely inelastic. Because if it were, then F elastic would be 0, and the total cross section would also be 0. Ballantyne, in his book on quantum mechanics, makes the remark that even a black hole has an amplitude for elastic scattering. I mean, you think a black hole's devouring everything, but they don't. They can't. By the optical theorem, it's impossible, because if they devoured everything, they would be totally inelastic, and that's not how it works. Okay, there are other consequences. I think I'll have a homework problem that involves this formula and some inelastic scattering that you can understand this situation better. All right, this is all I want to say about the optical theorem. Are there any more questions or any questions about it? It's interesting physics, and the fact that it's exact is something that attracts a lot of attention. Any questions about this before we move on to the next topic?
I thought that if you had two channels, say one inelastic, one elastic, the total cross section, which is the sum of the two individual cross sections, is that not the case?
That is the case, but that goes into sigma tot. So sigma tot sums over all channels, but the f of 0 only involves the elastic channel.
I see. Okay. Thanks.
Yeah, that's the point. Okay. All right.
Is there an F for inelastic scattering, or is there not
Yeah,
even an F?
the inelastic channels also have their scattering amplitudes as well, and the fluxes and so on, but they don't contribute to the F that appears here.
Okay.
You see, the inelastic channels don't interfere with the incident wave. That's the reason why. You can't get an interference between a proton wave function and an electron wave function.
Yeah. Okay. Thank you.
That's the idea. It's an interesting notion. You can't even get an interference between a spin up electron and a spin down electron. If you change the internal quantum numbers of the system, you don't get interference anymore. In an important sense, well, I don't want to digress, so I'll skip that. All right, anyway, so that's the optical theorem. All right, so we're not done with scattering theory. There's more to do, fair amount actually. And the rest of what we need to do with scattering theory involves Green's functions. So I want to have the rest of tonight's lecture and carrying it on Thursday on the subject of Green's functions. So let me say some things about that. In the first place, I'm going to assume that you have experience with Green's functions from Physics 209 last semester. If there's some of you who aren't physics students, or for some reason you didn't get that, let me know, and I'd be glad to talk to you about it. By the way, I also wanted to say, if there's any students that are need filling in on background like definition of cross section and stuff like that, please contact me. I'd be glad to meet with you, outside of office hours. Office hours tend to be hogged up by homework, and I'd be glad to go over that material with you. But in any case, I'm basically going to assume that you kind of know what Green's functions are. So let me just give an introductory blurb to it. So if we have a typical linear wave equation that occurs in physical applications, let's say there's a linear operator L and there's a wave function psi of x and t, say, equals 0. If the wave equation looks like this, it's said to be inhomogeneous. That's the mathematical terminology. To say it's inhomogeneous means that, it's homogeneous. To say it's homogeneous means that the psi occurs in all terms of the equation. On the other hand, if you had a wave equation, a wave field, let's call it psi, which was being driven by a source, let's call it S of x and t, which is a source, then in mathematical language, this is inhomogeneous because the psi doesn't appear in the S. So inhomogeneous wave equations occur in, or linear equations occur in E and M. Is there a question? Did I hear a question? Inhomogeneous wave equations occur in E and M. That's why you might have seen it in 209. For example, the Maxwell's equations can be put into a form that looks like this. We have the D'Alembert operator acting on the vector potential is equal to the current. It looks something like this. The D'Alembert operator is equal to 1 over c squared d squared dt squared minus del squared. It's the wave, it's basically the wave operator. And I'm emitting constants here like mu naughts and epsilon naughts, and I'm just looking at the vector potential here instead of the scalar potential. But this is roughly the structure of the wave equation you need to solve when you have sources, time-dependent sources and currents in Maxwell's equations. Now, how do we solve an equation like this? What we do is we use a Green's function for the D'Alembert operator. Green's function is a function of two space-time points, and we call them x and x prime. The x here stands for x and t, and the x prime stands for x prime and t prime. The x and t we can call a field or observational point, and the x prime and t prime we'll call a source point. Sometimes you might call these initial and final as well, something like that. But anyway, G depends on a pair of space-time values, of which the second one is the source, and the first one is the field point. So what we require is a Green's function that is required to satisfy the following differential equation. The D'Alembert applied to G, where the D'Alembert operator acts only in the field dependence, gives us a four-dimensional delta function in x and x prime, where the x prime is a source dependence of the Green's function. If we can find such a Green's function, then the solution A of x is given by an integral dx prime. Excuse me, let's do it right. The general solution of our equation here is that A of x is equal to what I'll call a sub h of x, which I'll explain in a moment, plus the integral over the source dx prime. Is really a four-dimensional integral here of g of x prime times the j, which is the current evaluated at x prime. The current here is the source. The current here is the source of Maxwell's equations. Okay. What is AH? AH is a solution of the homogeneous equation. Any solution of the homogeneous equation. If there are no sources, then AH is a solution of that. Now, the following standard technology with Green's functions, this formula I wrote down here, it's in schematic form, but this is the correct structure of the formula, gives us the general solution of this inhomogeneous wave equation that we started with. It's a general solution for the following reason. First of all, we need to show that it's a solution. To do that, let's apply the D'Alembert operator to both sides. Well, the D'Alembert acting on A just gives me D'Alembert of A. This is evaluated at x. The D'Alembert of A homogeneous is 0 because that's what we mean by that. As far as the integral is concerned, we get d4x prime. The D'Alembert of G, by the definition of a Green's function, is a delta function, delta 4x, x minus x prime. This is multiplied by the source, j of x prime. And so you can do the integral and you get j of x. And so what we get is D'Alembert A is equal to j. That's the original equation. Okay. So this is the structure of how Green's functions are used. Now, I think it's useful to think of a problem. I think it's useful to get a physical picture of this. I think it's very useful to imagine a specific problem in electromagnetism where we're, let's say, scattering radar waves off of a metal obstacle. This is what radar people do all the time. What's the physics of it? We launch an electromagnetic wave at a conductor. We launch it at some distance. Electromagnetic wave has E and B fields that are oscillating. When they reach the conductor, the electric fields, what do? They induce a current in the conductor because J equals sigma E. The current, the electrons in the metal respond to the electric field and produce a current. Well, those currents then radiate waves, new waves. Those are the scattered waves. And those scattered waves then contribute to the electromagnetic field. If we imagine continuing this process, let's say with the incident beam turned on, continuing to be turned on, then the scattered wave and the incident wave combine together ultimately to form a kind of a steady state. Of course, it's got an outgoing front that moves away from the scatterer, but it creates a kind of a steady state. And in that steady state, the electromagnetic field is the sum of the incident wave plus the wave produced by the currents in the metal. The currents in the metal, they're governed by Ohm's law. So there's J equals sigma E, like this. This E is the total E. It's a total E from both the incident wave and the scattered wave. But the currents produced are the sources only of the scattered wave. Okay. So let's take our wave equation. The original wave equation we've got is D'Alembert A is equal to J. I'll leave the arrows off now. And let's put in J is equal to sigma E. And E, by the way, is equal to some operator times A, like so. And I'll absorb, it's basically a differential operator. I'll absorb that into the sigma. Let's just write J is equal to sigma A, if you'll allow me to do that, because I'm being very schematic here tonight. And if we do this now, what we have is an equation that D'Alembert A is equal to sigma A. And what you see is an equation that was originally, this part of it, was originally inhomogeneous from the mathematical standpoint, has now become a homogeneous equation in which the right-hand side, the source term on the right-hand side is now related to the incoming field. Okay. So in scattering problems like this, it's something of a matter of opinion whether or not we're dealing with an inhomogeneous equation or a homogeneous one. Now we can do something like this, similar to this with the Schrodinger equation. For the scattering problems we're interested in solving the usual Schrodinger equation in 3 dimensions. That's the problems we're talking about here. So our Schrodinger equation is H0 plus V acting on psi of x is equal to E times psi of x. That's what we want to solve. We want to solve it for positive energies. And the H0 here is the free particle Hamiltonian p squared over 2m. That's the basic thing we want to solve. Let's rearrange this equation and write it as E minus H0 acting on psi of x is equal to V times psi of x, V of x times psi of x. And let's compare this to what we had with the electromagnetic problem. D'Alembert A is equal to sigma times A. What you can see is that what we have in both cases is a free particle operator. The D'Alembert is a free light wave operator, an unknown field like this, a right-hand side that can be interpreted as a source, but the source is actually being driven by the incident wave. Actually, it's being driven by both the incident and the scattered wave. And the scattered wave is produced by the currents in the scatterer, which are induced by the total wave field. We can make a similar interpretation here in quantum mechanics. It's as if the potential plays the role of the conductivity, and the psi here plays the role of this. So it's like the wave function psi induces, in effect, charges or currents to move or something. You can think of it that way in the scatterer, which then radiate the scattered wave. So I'm going through all this for you because this gives you, in my mind, it gives you a vivid physical picture of what's happening. And all these formulas involving Green's functions, it helps a lot to have these kind of pictures of what's happening with these waves. All right, so that's an introduction then to Green's functions and how they're used in scattering theory and how and what the intuitive picture is that lies behind it. So this motivates then the writing the Schrodinger equation in this form, which isn't much of a change of the original Schrodinger equation, and interpreting the right-hand side of the equation as if it were a source. The Schrodinger equation in the normal sense of the word is intrinsically a homogeneous wave equation. The psi appears in all the terms. We don't normally have source terms. But with this trick that we've done here, we're going to interpret the right-hand side as a source, even though it's got a psi in it, which makes it overall homogeneous. So let's take this as motivation then for studying the Schrodinger equation with sources and the corresponding Green's functions that are needed to solve them. For the time independent problem, we'd have E minus H0 acting on psi of x is equal to some source psi of x. In order to solve this, we're going to need a Green's function for the operator E minus H0. I'll call these energy dependent Green's functions, and we'll talk about them at some length in the next lecture. Tonight we don't have enough time to do it. What I want to say though is that in order to arrive at energy dependent Green's functions in quantum mechanics, we need to make an excursion through time dependent Green's functions in quantum mechanics first. So let's talk about time dependent Green's functions in quantum mechanics and put these energy dependent Green's functions on hold. For that purpose, let's talk about a time dependent Schrodinger equation with a source term. Let's write it this way: IH bar dt minus HX on psi of x and t gives us a source of x and t, like so. I'll make this a 1D problem like this, so I'll take the arrows off. And for the Hamiltonian, let's say that it's minus h bar squared over 2m d squared dx squared plus v of x and t. We can make it a 1D problem and allow the potential to depend on time because there's no reason not to. Let's say that we want to solve this problem. In order to do so, we require a Green's function. And I'll call a Green's function f, call it f like this. It depends on x and t and x prime and t prime. As I explained before, the first set we'll think of as the field pair of space-time points, and the second pair we'll think of this as the source. And f is required in order to be a Green's function, in order to qualify as a Green's function, we'll demand that f satisfy the equation IH bar partial with respect to t acting on f, IH bar partial with respect to t minus the Hamiltonian acting on f at x t and x prime t prime shall be equal to IH bar times delta x minus x prime times delta t minus t prime. Okay. We will call any function that satisfies this equation a Green's function for the time-dependent Schrodinger equation. And if we find such a function, then the general solution of this equation here can be written this way, is that psi of x and t is a homogeneous solution, psi homogeneous of x and t, plus 1 over IH bar integral from minus infinity to plus infinity dt prime integral dx prime f of x and t, x prime and t prime times the source evaluated at x prime t prime. For psi h satisfies IH bar ddt minus the Hamiltonian on psi h of x and t equals 0 is the solution to the homogeneous equation. All right. So any f that satisfies this any f that satisfies this equation will be regarded as a Green's function, and we can use any such f to obtain a general solution like this. I know that this is the general solution of the original equation because if I have any two solutions of an inhomogeneous equation with a source, and if I subtract them, what I get is a solution without the source, as to say a homogeneous solution. So therefore, if I have one specific solution of the inhomogeneous equation, then any other solution can be generated by adding a homogeneous solution. And that's what this formula captures. So this is indeed the general solution of the original equation, regardless of which Green's function we choose. There are many possible solutions of this equation, many possible Green's functions, but they'll all work for creating the general solution. So notice I'll just make a couple of comments and then we'll quit. So notice what's going on here is the Green's function itself, as you can see, satisfies an inhomogeneous equation. It's one with a delta function driving term on the right-hand side. This H, by the way, acts on the field points, not the source points. So the statement is that if we can solve the inhomogeneous equation with a delta function on the right-hand side, then we can solve the inhomogeneous equation with an arbitrary source term. And roughly speaking, the idea is you just take the source term and you write it as a linear combination of delta functions by writing as an integral over, a variable. And then each one of those delta functions contributes f. And so then you have to add up all those different f's to get the answer for the total source s. And that's just what this is. These different f's are weighted by the s, you see. The integral is adding them all up, and that gives us this integral term. So that's the idea. Okay, so that's just an introduction to this. Where we're going to, this is where we'll start next time. We'll start with the specific time-dependent Green's functions, which are useful in quantum mechanics, not just this general F. We'll deal with specific ones, and then we'll work through them, and then we'll work on to energy-dependent Green's functions, and then we can get back to scattering theory. That's the strategy. That's all for tonight. Are there any questions?
So just to be clear, we're doing all this because eventually we're going to say our source is the potential times the wave function.
That's right.
Okay.
That's right. Yep, that's where we're going.
So there would never be an actual like physical inhomogeneous Schrodinger equation, right? Because that would mean we'd have probability appearing out of nowhere somewhere.
Yeah, that's right. That's definitely an issue if you're talking about the ordinary Schrodinger equation. I would never want to say never because people do a lot of things with the Schrodinger. They put in damping. I don't know. There's all kinds of things that can be done with it. But yes, what you're saying is right. The basic idea.
Okay, thank you.
That's good. Any other questions? All right then. If there's no other questions, let me remind you that if you have any questions about basics of scattering theory or anything else that you Green's functions or whatever, please contact me and I'd be glad to talk to you about it. So I shall now turn off screen share, and then I shall turn off recording.